Z4 is a set of 4 boxes. Each of the boxes is a set of numbers. So there's 2 ways to define it. One is the partition method that I showed you today, that I actually am taking all the integers and packing them into 4 boxes. So the objects in Z4 are boxes. The objects in Z are not boxes. Another way to define it, I think Fraley defines it like this. He uses equivalence classes, and he puts everything that has the same remainder in a box that's equivalence class. You can either use partition method or equivalence classes. So again, the objects in Z4 are an entire set, and you're comparing them to integers. It's not a subgroup. David? You can probably understand that even more, like with Z4 and Z8, right? You can see, well, and one of them, when you add, you mean you're adding mod 8, and the other one, when you're adding mod 4. So the Z4 cannot be a subset. Sean, I'm not sure what undergraduate text you use, but have you ever seen people do this? I'm typing this out. Have you ever seen them describe the Z, that's not a Z, like Z4 would be 0, 1, 2, 3. So Z4 is the set 0, 1, 2, 3, but they put little hash marks around it like so. I don't know if you've ever seen that kind of notation before. Hungerford uses it. They're very careful to use this notation so that students can see that they're not talking about a single integer. They're talking about each one of the objects in Z4 is a whole set. Ryan, we had a little bit of this in PDEs. In PDEs, we had the L2 functions, and actually they ended up being sets inside the sets of functions, equivalence classes. So we had something like this weird in Lebesgue integration. Something similar there. Okay, good. All right, similar stuff. All right, on to dihedral groups. Talking about weird, let's go to dihedral groups. So you've seen the triangle now. I have now the square, and I've labeled the 1, 2, 3, 4. As before, I remind you that when I have the little subscript here, I mean that there's four vertices. So one way that you can talk about the different rotations and symmetries of the dihedral group of 4 with 4 vertices, you can take these and see where they get mapped to. For example, in this case, if I leave things alone, 1 gets mapped to 1, the vertex 2 gets mapped to 2, 3 gets mapped to 3, and 4 gets mapped to 4. So notice I took the red vertices and I put them on top here, and I put the green vertices on bottom, indicating that 1 gets mapped to 1, 2 gets mapped to 2, 3 gets mapped to 3, 4 gets mapped to 4. This is called a permutation, and in this case I haven't really rearranged anything, but it's just a rearrangement of these first 4 vertices by doing this mapping. Let's do a different mapping so you can see what happens. This is what I'm calling mu1, and I tried to take the notation, unfortunately, from Fraley, but I ended up in trouble right away trying to use the notation from Fraley. It's a little clunky, but because I wanted to use something different for symmetry than I do for rotations. But what I did is I reflected over see the line of symmetry. It's really light. I think it's showing up light on this PDF, but you see the line of symmetry I drew between 1 and 3 here. Can everybody see that? Because I can barely see that. It might be because I'm older. Okay, young eyes. Okay, then what I'm going to do is I'm going to fold over this line. So 2 now will move to 4 and 4 will move to 2, but 1 and 3 stay put. So I get this new transformed square. Where 2 was, it got mapped to 4. So 4 is written right underneath 2. 1 and 3 stayed fixed. So I put the 1 and 3 in place here. And the 4, the old red 4 is now a 2. So the 4 gets mapped to 2. And if you recall from undergrad algebra, it might have been a long time ago, this is the standard way we write permutations. They look like matrices. And the first time you take an undergrad abstract algebra class and you see this, you are also taking sometimes linear algebra at the same time, or you just took linear algebra and you get very confused. At least I did. Why is she talking about matrices in here? Here's another one. I'm going to reflect now over the other side. I'm going to take the 2, 4. In this case, when I reflect, when I fold over, the 2 and the 4 swaps place. I'm sorry. Actually, the 1 and the 3 will swap places here. 2 and 4 swap places here. It should have been the other way around. And the 1 and 3 stay. Yeah, I did it right. 1 and the 3 swap places. I shouldn't second guess myself because I wrote this when I was... And the 2 and the 4 stay fixed. So 1 and the 3 swap places, and so this is the... Don't listen to what I say. Just watch what the screen is saying. I wrote this one in the morning. Some morning a while ago when I had a clear head and a cup of coffee. I'm making up all kinds of things right now. Give me 4 more hours and I'll make up a whole bunch of stuff. I can write theorems that don't make any sense at all. Okay, so again, this is the same idea. 1 stayed put, 2 get mapped to, because 2 stayed put, and 4 stayed put, 1 swapped to 3, and 3 swapped to 1. So I think I have the indices down here on the bottom. And I'll correct that on the PowerPoint that's up online. Mu3, similar idea, but here there's a line of reflection that's different than a diagonal. I'm going to fold over this line here. So 1 and 2 swap places and 4 and 3 swap places because I'm folding over this line, which your young eyes can see. My older eyes can barely see. So you get 1 to 2, 2 to 1, 3 to 4, and 4 to 3. See, this 4 now gets mapped to this 3. And so forth. I can go through every one of these. I go through every one of them slowly on this PowerPoint so you can see them, and one time incorrectly. So here, this is a fold over this line. The 2 and the 3 get swapped. The 1 and the 4 get swapped. So now I have 1 goes to 4, 2 goes to 3, 4 goes to 1, and 3 goes to 2. Again, in the notation that Fraley is using, rotations are, I'm going to label them with rows. And I think this might be a copy and paste error. Yeah, that line shouldn't be there in the middle anymore. So now I'm going to rotate once. So this should have a rotation symbol here. So picture the Microsoft Word rotation symbol here going around. So rotate around once, and see this line here? It didn't disappear because my eyes didn't see it. So rotate around once. If I rotate clockwise once, then what's going to happen is this 3 is going to move up here, the 2 is going to move here, the 1 will move down here, and the 4 will move here. So the new clockwise rotation gave me this guy. Pictures are just fine, and the vertices are correctly labeled. If I look at what happened, 1 ended up going to 2, 2 ended up going to 3, 3 ended up going to 4, and 4 ended up going to 1. So 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. So this is not the possible set of all permutations of 4 elements. These are only the ones that I can get from rotations and symmetries from the square. Here's row 2. This is rotating twice clockwise. If I rotate twice clockwise, I get this guy right here. And we did this last time with the triangle, so I think everybody's starting to get more comfortable with doing this. So in this case, you can see again, 1 went to 3. So here 1 goes to 3. So we can represent this rotation in this form that I have, which is reminiscent of the permutations that you might have seen in undergrad. Third rotation, and you know what's going to happen with the fourth rotation. I'm going to be right back to where I started. And someone else, not me, figured out what all the different combinations of what happens if I do a symmetry first, reflection first, and then I rotate next. What will I end up with? So as we did for the triangle last time, someone went and did that. God bless them. They went and did that for the dihedral group of 4 elements. And this is the full Cayley table that you get. It's scary. What you'll notice is I actually ran out of time last time, but I wanted you to see that it's not commutative. So not everything commutes. I think we can just pull a random one to see that. Let's do row 1, mu 3. Row 1 star mu 3 gave me mu 2, but mu 3 row 1 gave me mu 1. So it's not commutative. But some of them are. So take a look at this diagram here and look at number 2. Believe it or not, I think we're actually going to run out of time here. What I'd like you to do is just do play. It's not heartbreakingly difficult. Go through this D4. This PowerPoint is up online, and when you turn in on Wednesday, pick out all those elements. And what we know already is if I just work with commuting elements, there's nice structure. That one problem that we had where x star x was equal to e, you see you have nice properties there. So I'm working with only the commutative elements from this table. So let's see if we can find one. Anybody find one yet that commutes? I think mu 3 obviously commutes with itself, but mu 4 mu 3. I don't get a commutative piece there. Okay, so all the rotations are going to commute. So I think they might be easy to pick out. So then put them into their own Cayley table, and you'll find that if you look at just the commuting elements, you can create that Cayley table. And if you can create that Cayley table, it means that you have a subgroup. That subgroup is always a subgroup. It's called the center of the subgroup. So if I take the set of elements from an original group and look at just the elements that commute, and I call it Z of G, that special subgroup is called a center.